In this video, we're going to be taking a look at a momentum and impulse problem that's a common lab, where we have a cart attached to some sort of elastic band that's hooked up to a force sensor, and then in addition to it, there's a motion detector on the opposite end here. So this brings up a bunch of good graphs that are related to momentum and impulse. And the first one we're going to look at is the force versus time graph. So generally, you're going to get some sort of spike because as the cart is moving farther and farther away, you get more and more stretch, more and more opposing force from the elastic band because it's trying to pull back to its equilibrium position. And then as it pulls it back, that tension in it is going to decrease. So you typically get some sort of spike and some sort of triangle there. Now, we have two different formulas. We have force times time equals impulse, and then we also have impulse is equal to mass times delta V being the change in velocity. So obviously this one is more closely related to the force and time. And what you're going to do is you're just going to simply find the area of this triangle here. Now, most of the time you could just do 1/2 base times height. Sometimes you might have to split it in half and make two right triangles. I would say that's typically not the case. So if we go ahead and do 1/2 base times height, we have 1/2. The base goes from 0.3 to 0.5. So technically it's 0.5 minus 0.3. So it's 0.2. And then times the height. And it looks like we have a height of 10 newtons. So we have a nice impulse of 1 kilogram meter per second because 1/2 times 0.2 is 0.1, 0.1 times 10 is 1. So that is our first method of solving for impulse. Now the second one is taking a look at our kinematic curves. Now if you're taking a look at a velocity versus time graph and a position versus time graph, you can find what you need in either one. So let me go ahead and sketch what both of them would look like. For a velocity graph, you would have something that maybe looks fairly consistent, and because it's becoming closer to the motion detector, that's going to be going in the negative direction. So we'll say it's sort of like a shaky negative. And then when the elastic band stretches out to its maximum, it's going to eventually make it come to rest. So it's going to head towards 0, come to rest momentarily, and then it's going to speed up in the positive direction, which is away from the motion detector. And then this is going to be your initial velocity, and then this is going to be your final velocity, and then we kind of have a bunch of acceleration in the middle there. Now for our position versus time graph, it's starting a little bit farther from the motion detector and becomes closer to it, so it's going to have a negative slope. It probably won't quite reach a position of 0 because that would mean it's touching the motion detector, and then it'll have some sort of curve for the acceleration, so it's going to slow down and then speed up, and then the slope is going to start to maybe level out a little bit more. So what you can do there is you would highlight a certain portion, and this slope would give you your initial velocity, and then highlight this specific portion over here, and then this slope would equal your final velocity. So there's a couple ways you could do that. This one probably tends to be a little shaky, so you could possibly highlight that one and then find the average or the mean of this section, and that might give you a little bit of a better value. So let's say, for example, this is going at about -1, and we'll say this goes at a +1. I'm sure the numbers aren't going to be quite that clean, but what you would do is you would take your mass of 530 grams, and you would divide it by 1,000. So then you can make it 0.53 kilograms. And then we can go ahead and use our second formula, which is mass times VF minus VI. And then we have a mass of 0.53. Our VF would equal about 1. And then we would subtract our VI that is about -1. Okay, so 1 minus -1 is going to be the same thing as adding. So that's going to come out to 2. And then 2 times 0.53 is 1.06 kilogram meters per second. So we have two methods of finding the same thing. Because in its experimental values, they're probably not going to come out perfect. It looks like there's a 6% difference here between our FT method and our M delta V method. But those are the two different ways you can analyze the graphs and calculate your impulse of the cart because of the force applied by the elastic band. So I hope that was helpful to you. Thank you for watching and listening.